My name is Sabari Sento, and this is our project. As a future architectural engineer student at UT, allow me to explain the physics of how this suspension bridge works. To begin with, we have suspension cables that provide support for the beams on the sides of the bridge. This allows for more tension to be placed on the center bridge so that when this collapses inside, the tension provides an opposite force which keeps the bridge from collapsing. My name is Sabari Sento, and this is part 2 of explaining how the bridge works. So here we have the arch of the bridge. This provides for extra support on the beams of the bridge so that they do not collapse when extra pressure is placed on the center beam. My name is Sabari Sento, and this is part 3 of explaining how our suspension bridge works. Here we have simple machine pulleys. This allows for the drawbridge to be pulled up and down with ease because the pulleys enable for a force to be extracted on the centerfold of the bridge. My name is Sabari Sento, and this is our 4th and final part of explaining of how our suspension bridge works. So as I mentioned previously, we have pulleys here which pull on the drawbridge. So when this drawbridge is pulled, I broke it. So we resolved our technical issues, but as I was mentioning before, the pulley pulls on the end of the drawbridge, which applies torque on it. The reason why we have it at the end is because torque equals force times radius perpendicular. So by maximizing the radius of the lever arm, we also maximize the torque. Furthermore, the torque that we needed to counteract was the torque of the bridge itself. We calculated this, which will be shown later in our video, but we calculated this by finding the mass of the bridge itself and the length of the midway point, which the center of mass is located at. My name is Sabari Sento, and as a future UT student who's going to study architectural engineering, thank you for allowing me to explain the physics of our suspension bridge, also known as the Golden Corral Bridge. My partners were Jacob Van Benthuizen and Serge Frazier, who is the cameraman of this video.
Alrighty, so I'm going to go ahead and explain the physics of this bridge from just a different perspective. So the key physics concept behind this entire bridge design is torque. So as Sabari mentioned, torque is going to be the cross product between radius and force. And almost every part of this design involves some sort of torque. So first let's talk about the role of the suspension cables in the design of the bridge. So anytime you put a weight in the center of the bridge, it's actually going to exert a torque on the columns. And that's because in theory, you're going to have a point of rotation at the bases of these two columns. And because the center plank rests on a point on the columns, it's going to exert a torque on the columns. And this torque is going to have a tendency to bring them in towards each other. And of course, you know, in a bridge, it kind of sucks whenever two columns collapse in on each other. So you're going to have to counteract this torque somehow. And so we installed suspension cables, which effectively provide a torque due to tension in the opposite direction of the torque or I guess the applied torque, you could call it, of the weight. So the torque due to tension is going to pull those two columns out, counteracting the torque going in, and thus stabilizing the bridge. So now I'm going to talk about the actual draw part of the drawbridge. Alrighty. So, in order to raise this center point of the bridge, you're going to have to exert torque. And just writing out the relationship again here, if you want to maximize your torque, you're either going to have to maximize your force or maximize the length of your lever arm, which is R. Now, we don't want to maximize the force because obviously in a real life scenario involving a drawbridge, you're going to want to minimize the amount of force you actually put into it, depending on whether or not a machine is raising the bridge or a person is raising the bridge. So instead, you want to maximize the radial component of your torque. And that's why we went ahead and attached the strain all the way at the very end of the plank, because that's going to maximize the length of the lever arm, which is going to have a pivot point on this right column right over here. Now, this strain is going to apply a torque. So you have your force due to tension right here. And it's going to apply a torque at the very end, which is going to allow us to counteract the torque of the center of mass of the bridge, thus allowing us to actually pull the bridge up and raise it. So yeah, that's the physics. Thanks, guys.